Hello everyone, my name is Octavio Garcia. I'm going to present the work thermal evaluation of the mixed tunnel type solar dehydrator under different operation conditions. I'm the leader of the solar drying group of the Institute of Renewable Energy of the National Autonomous University of Mexico. The economic and social development of countries depends on energy resources, and in this sense, Mexico has a great potential in terms of the use of alternative energies, such as in the case of solar energy. Despite some barriers, it has been predicted that renewable energy technologies are a suitable strategy for food drying that brings some benefits such as low cost, high efficiency, increased employment opportunities, etc. In tropical countries, the drying of agricultural products has conventionally been carried out in the open sun drying. The disadvantage of open sun drying is the uncontrolled heat transfer to the produce and a slow drying speed, as well as losses due to fungi, insects, birds, rodents, unexpected rains, and other meteorological effects. As a result, the quality of the product is very poor and they cannot be compete in the international market. Methodology: in this work, the thermal evaluation of the mixed tunnel type solar dryer was carried out under different operation conditions. The test was carried out in the month of February to 2023 from 10.50 to 14.50 hours. It is worth mentioning that there are 2 hours before and after solar noon, which was at 12-15 hours. Measurements of temperature and solar irradiance, humidity, and the inlet mass flow rate were taken every minute, while air velocity measurements at the outlet of the dryer were taken every 50 minutes. The tunnel-type solar dryer consists of 4 solar air heaters connected in series, each one with 1.8 square meters area. They are connected to a 550 watts direct current fan that works with a photovoltaic array of 2 panels of 350 watts, which send the hot air from the solar collector array to the interior of the dryer. The drying chamber is made of 1-inch steel profiles and has 6 millimeters polycarbonate cover on the walls, allowing direct solar radiation to enter the chamber. So the heat gains inside the dryer are a combination of the heat gained by the solar collector array plus the solar irradiance entering directly through the polycarbonate. The tunnel-type drying chamber length is 5.5 meters and it has a capacity of 40 aluminum trays of 60 per 43 centimeters. The measurement equipment used is as follows: 6 PT1000 temperature sensors, 2 pyranometers, 1 air mass flow meter, 1 anemometer, 4 humidity sensors, glass beakers, and balance. The location of these sensors are shown in Figure 4. Two different tests were carried out in the tunnel-type solar dryer in order to evaluate the system thermal performance. The first 4 ones were from 10:50 hours until 14:50 hours. Each test was carried out at different fan velocities. Temperatures, solar irradiance, air mass flow rates, and humidity were measured. In the test of water evaporation, the dryer was filled with 20 trays with a volume of half liter of water, having an initial volume in the tunnel-type solar dryer of 20 liters. The instantaneous thermal efficiency of the solar collector array was determined by equation 1, where the numerator indicates the amount of instantaneous energy transferred to the air, while the denominator is the total instantaneous energy received by the sun in the plane of the solar collector array. These calculations are made every minute, and the values obtained have been graphed. The drying efficiency was calculated with equation 4, where the numerator is the energy required to evaporate the water and the denominator is the energy used to achieve this purpose, which is the sum of the energy from the sun received in the solar collector array plus the energy received by the sun through the polycarbonates of the dryer plus the energy used by the fan. Total insolation for the solar dryer is calculated with equation 9. The graph shows the temperatures obtained in the test using the fan at 4,000 revolutions per minute, which gave an air mass flow rate of 4.14 kilograms per minute. The maximum temperature was reached at the outlet of the solar collector array with an approximate value of 70 degrees centigrade, and a minimum temperature inside the dryer was 42 degrees centigrade, with an average temperature of 55 degrees centigrade inside the drying tunnel, more than acceptable temperatures for drying food. The following graph shows the instantaneous thermal efficiency of the solar collector array evaluated every minute, where an average thermal efficiency of 46% was obtained with an average solar irradiance of 983 watts per square meter and an average ambient temperature of 31.4 degrees centigrade during the test. To be able to clearly have the distribution of dries in the dryer, the numbers 1 to 8 represent the doors of the drying tunnel, number 8 being the closest to the hot air inlet of the solar collector array, and the row with the numbers 1 to 5 represent the vertical position of the dries. The following table shows the behavior of the dryer by means of a color map, where the red color represents where more water evaporates and the green color where the least amount of water evaporates. At the end of the test, the water contained in each dryer was measured to see how much water was evaporated. The values obtained in milliliters can be seen in Table 1. As expected, the dryers that evaporate the greatest amount of water are those in the first row, which have direct radiation from the sun, and in column N, where there is hot air coming from the solar collector array. At the end of the test, a total of 11.6 liters were evaporated, 58% of the total water deposited at the beginning, and the tunnel type drying efficiency obtained was 60%. The graph shows the temperatures obtained in the test using the fan at 3,000 revolutions per minute, which gave an air mass flow rate of 3.24 kilograms per minute. The maximum temperature was reached at the outlet of the solar collector array with an approximate value of 72 degrees centigrade, and a minimum temperature inside the dryer was 39 degrees centigrade, with an average temperature of 56 degrees centigrade inside the drying tube. The following graph shows the instantaneous thermal efficiency of the solar collector array evaluated every minute, where an average thermal efficiency of 42% was obtained with an average solar irradiance of 1003 watts per square meter with intermittent partial cloudy from 12:45 to 14 hours and an average ambient temperature of 31.5 degrees centigrade during the test. The water evaporated in each dry at the end of the test in millimeters can be seen in Table 2. At the end of the test, a total of 11.7 liters were evaporated, and the tunnel type drying efficiency obtained was 50.78%, very similar result to those obtained with 4,000 revolutions per minute. The figure shows the temperatures obtained in the test using the fan at 2,000 revolutions per minute, which gave an air mass flow rate of 2.1 kilograms per minute. The maximum temperature was reached at the outlet of the solar collector array with an approximate value of 77 degrees centigrade, and a minimum temperature inside the dryer was 43 degrees centigrade, with an average temperature of 57 degrees centigrade in the drying tunnel. Higher temperatures than the previous tests are reached due to the lower airflow in this test. The figure shows the instantaneous thermal efficiency of the solar collector for 2,000 revolutions per minute, where an average thermal efficiency of 33% was obtained with an average solar irradiance of 1,012 watts per square meters, and an average ambient temperature of 31.3 degrees centigrade during the test. As expected, the efficiency of the solar collector array was significantly reduced due to the low airflow, and as a consequence, lower convective heat transfer coefficients are obtained. The water evaporated at the end of the test in milliliters in each tray can be seen in Table 3. At the end of the test, a total of 10.3 liters were evaporated, 51.5% of the total water deposited at the beginning, and the tunnel type drying efficiency obtained was 40.64%. The graph shows the temperatures obtained in the natural convection experiment, where a maximum temperature of 63 degrees centigrade and a minimum temperature of 38 degrees centigrade were obtained, with an average temperature inside the drying tunnel of 52 degrees centigrade, with an average solar irradiance of 991 watts per square meters. Higher temperatures than the previous test are reached due to the natural convection inside the dryer. At the end of the test of natural convection, only a total of 6.3 liters were evaporated, 31.5% of the total water deposited at the beginning, and the tunnel type drying efficiency obtained was 9.64%. Much lower values than those previously obtained due to not using the fan and the solar collector array. The following tests were drying chilacayote. The chilacayote is a type of pumpkin from the Cucurbitaceae family. The word chilacayote comes from the Nahuatl word chilacayotl, chilac, which means smooth, and ayotli, which means pumpkin. In other words, smooth pumpkin. It is a source of vitamin A, vitamin C, and iron. Moreover, for a medical point of view, this fruit has been related to hypoglycemic properties. Chilacayote drying test was carried out by filling the dryer with 300 grams of chilacayote in 5 millimeter slices in each tray, giving a total of 12 kilograms of chilacayote to be dried. The test was obtained for fan speed of 4,000 revolutions per minute and 2,000 revolutions per minute. Three drying kinetics of chilacayote were obtained for each different speed. One drying kinetic at the beginning, one at the middle, and at the end of the tunnel as shown in figure 50. In the figure, we can observe the two drying kinetics of the chilacayote where in the 4,000 revolutions per minute test, it started with an average humidity of 90%. And it is observed that at the beginning of the tunnel, the product was dried in 6 hours, until reaching a final humidity of 10%. At the middle of the tunnel, it took 7 hours to dry and reach a humidity of 10.5%, and at the end of the tunnel, it took 8 hours to reach a humidity content of 11.9%. For the drying kinetics of the chilacayote in the test of 2,000 revolutions per minute, it started with an average humidity of the product of 91%, where at the beginning of the tunnel the product was dried in 8 hours, until it reached a final humidity of 13.2%. At the middle, it took 11 hours to dry and reach a humidity of 13.2%, and at the end of the tunnel, it took 11 hours of drying to reach a humidity content of 14.2%. On average, it took 3 more hours to dry at 2,000 revolutions per minute, and the final humidity that was obtained with 4,000 revolutions per minute was not reached. At the end, the dry product was made into flour. The drying efficiency obtained for the drying of chilacayote at 4,000 revolutions per minute was 9.56%, and for the test of 2,000 revolutions per minute, it was 5.04%. Efficiency at 2,000 revolutions per minute dropped by almost 50%, due to less airflow within the test and the lower mass and heat transfer coefficients that result from this. Conclusions. In the test with water, the amount of water removed in 4 hours with the fan at 4,000 revolutions per minute was 11.6 liters, 58.1% of the total water deposited at the beginning. An average instantaneous solar collector array efficiency was 46%, and the drying efficiency obtained for the tunnel type solar dryer was 16.04%. By counterparty, in the test with water in natural convection without fan and solar collector array, the amount of water removed was only 6.3 liters, 31.5% of the total water deposited at the beginning, and the drying efficiency obtained was 9.64%. The drying kinetics of chilacayote coincides with the behavior of the dryer in the test with water. The final moisture content of the chilacayote was 10.8%, with the fan at 4,000 revolutions per minute, and 8 hours of drying obtained a drying efficiency of 9.56%. For 2,000 revolutions per minute, final moisture content of 13.53% was obtained with 11 hours of drying and a drying efficiency of 5.04. As a conclusion, a tunnel-type solar dehydrator was designed, built, and evaluated in Temisco, Morelos for the hydration of agricultural products. According to the results obtained, different kinds of products can be dried, resulting in substantial fuel savings and environmental benefits. This work was financially supported by PAPIT project IN 103021, Solar Drying of Agricultural Products, and the CONACYT project 319188, Community Center for Solar Dehydration of Agricultural Products of Small Indigenous Producers of Hueyapan, Morelos. Thank you very much.